August 15, 1944. Outside the village of Dreux, 50 miles west of Paris, Major William Patterson of the United States Army Corps of Engineers stood in a wheat field that 6 hours earlier had been completely empty. Now, flexible steel pipes snaked across the ground like enormous serpents, pumping aviation gasoline at 2,000 gallons per minute into rapidly expanding storage bladders that resembled gigantic grey whales beached in the French countryside. Behind him, bulldozers carved roads that hadn't existed at dawn, their diesel engines roaring as they pushed aside centuries-old stone walls that had once marked property boundaries for Norman farmers. Crews assembled prefabricated tank farms with mechanical precision, each man performing specialized tasks learned through months of training that had transformed ordinary soldiers into industrial specialists. And overhead, the constant roar of Allied fighter bombers reminded everyone why this seemingly impossible construction pace mattered. Patterson checked his watch, a Hamilton timepiece his wife had given him before deployment. 18 hours since the first trucks had arrived, carrying equipment that most military engineers had never seen before the war. Already, they were pumping fuel to forward airfields that would support the drive toward Paris. The mathematics were staggering. In less than a day, his engineers had created fuel distribution capacity that traditional methods would have required 3 weeks to establish. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. What Patterson didn't know, watching his engineers work with methodical efficiency in that French wheat field, was that 15 miles to the east, German intelligence officers were frantically radioing headquarters with reports that defied belief. American forces were constructing major fuel installations faster than German engineers could destroy existing ones. The psychological impact was devastating German morale as effectively as Allied artillery was destroying their defensive positions. Oberst Heinrich Fischer, commanding the German forces near Dreux, had spent the morning studying intelligence photographs of the American construction through powerful field glasses. His engineering background from civilian life made the speed even more incomprehensible. Fischer had supervised construction of petroleum facilities in Romania before the war. Building comparable capacity had required months of work by skilled specialists. The Americans were accomplishing the same mission in hours using soldiers who appeared to be following simple assembly procedures. The speed of Allied fuel depot construction had become a strategic weapon that German planners never anticipated. Within 72 hours, Patterson's unit would have established a complete fuel distribution network capable of supplying 3 fighter squadrons and supporting the advancing Third Army's tank columns. The Germans had calculated that destroying French fuel infrastructure would delay Allied advances by weeks. Instead, American engineers were building replacement capacity in days, fundamentally altering the strategic balance of mechanized warfare. This transformation of military fuel logistics began not in France, but in the deserts of North Africa 2 years earlier, where American engineers first confronted the reality that modern mechanized warfare consumed fuel at rates that traditional supply methods couldn't sustain. The crisis that would revolutionize military fuel handling began in Tunisia during the spring of 1943, when the seemingly simple problem of keeping tanks fueled nearly derailed Allied offensive operations. General Omar Bradley's Second Corps was advancing toward Bizerte, spearheading Operation Vulcan, the final Allied push to eliminate Axis forces in North Africa. The offensive had begun with tremendous success. American armor had broken through German defensive lines and was advancing at speeds that exceeded all expectations. But their momentum stalled not because of enemy resistance, but because fuel trucks couldn't keep pace with advancing armor that was consuming gasoline faster than supply convoys could deliver it. Tank columns sat motionless for hours in the desert heat, while truck convoys struggled across damaged roads to deliver gasoline measured in 5-gallon jerrycans. The mathematics were devastating to contemplate. A single Sherman tank consumed approximately 150 gallons of gasoline for every 100 miles of operation. An armored division moving 50 miles required 75,000 gallons of fuel. Delivering that fuel in 5-gallon containers meant 15,000 individual jerrycans had to be transported, unloaded, and poured into tank after tank by hand. Each fueling operation took hours, as crews struggled with heavy containers under combat conditions. Columns that should have maintained offensive momentum instead became stationary targets, vulnerable to air attack and artillery fire. Lieutenant Colonel James Sullivan, 2nd Corps Fuel Supply Officer, watched advancing units halt repeatedly as fuel supplies dwindled, transforming what should have been rapid exploitation of tactical success into a series of stops and starts that allowed German forces to withdraw in good order. Sullivan documented the crisis in a report that would transform Allied logistics doctrine and ultimately change how mechanized warfare was conducted. Current fuel distribution methods are incompatible with mobile warfare, he wrote in prose that was stark in its implications. Tank columns advance faster than our supply trucks can follow. We're losing operational tempo because we can't deliver fuel efficiently to forward positions. The enemy is gaining time to establish defensive positions because our logistics can't sustain our tactical success. The report reached Washington in May 1943, landing on the desk of Colonel Louis Brereton at the Army Service Forces headquarters in the Pentagon. Brereton was uniquely qualified to understand both the military problem and potential civilian solutions. He had spent his pre-war career as a petroleum engineer for Standard Oil of California, working on pipeline projects across the American Southwest. He understood industrial fuel handling systems that could pump thousands of gallons per hour across vast distances, using technology that the military had never considered adapting for field operations. The military's reliance on truck transport and individual containers seemed primitively inefficient to someone familiar with industrial petroleum operations. Oil companies routinely moved millions of gallons across hundreds of miles using pipeline networks and pump stations that could be installed rapidly when circumstances required. The fundamental question was whether civilian petroleum technology could be adapted for military field conditions that included enemy fire, damaged terrain, and the need for rapid displacement. Brereton assembled what he called the Petroleum Supply Task Force, a group of civilian petroleum engineers temporarily commissioned as Army officers with the specific mission of adapting industrial fuel handling methods for military field conditions. The task force included experts from major oil companies who understood pipeline construction, pump station design, and bulk storage systems that could revolutionize military fuel logistics if properly adapted. Thomas Harrington from Texaco brought expertise in rapid pipeline installation developed during emergency operations in Texas oil fields. Robert Chen from Shell understood portable pump systems used for temporary installations during equipment maintenance. William Morrison from Standard Oil specialized in collapsible storage tanks developed for exploration operations in remote areas. Together, they would design systems that could establish major fuel depots with the speed and efficiency of civilian oil field operations. The breakthrough came from examining how oil companies handled emergency situations when natural disasters or equipment failures disrupted normal operations. During the 1938 hurricane that devastated petroleum facilities along the Texas coast, companies had rapidly deployed portable systems to restore fuel distribution to affected areas. Flexible pipelines could be unrolled across terrain in hours. Portable pumps could establish pressure without permanent installations that required weeks to construct. Collapsible storage tanks could create capacity wherever needed without excavation or permanent foundations. Harrington articulated the key insight during a task force meeting in June 1943 that would fundamentally reshape military logistics. Oil companies don't build permanent facilities for emergency operations, he explained, drawing diagrams on a blackboard that illustrated concepts foreign to traditional military engineering. They use portable systems that can be deployed rapidly and relocated as needed. Military fuel operations should work the same way. Instead of building permanent installations and supplying them with truck convoys, we should build mobile systems that advance with combat units. This required completely rethinking military fuel logistics from first principles. Instead of fixed installations supplied by truck convoys carrying individual containers, American forces would use mobile systems that could advance with combat units and provide continuous fuel flow without interruption. Flexible pipelines would replace truck transport for bulk movement across distances measured in miles rather than hundreds of yards. Portable pump stations would maintain pressure across long distances without requiring permanent construction. Collapsible storage systems would create capacity at forward positions that could be established in hours rather than weeks. The first prototype systems were tested at Fort Belvoir, Virginia, during the summer of 1943 under conditions designed to simulate combat operations. The results exceeded all expectations and validated the fundamental concept. A complete fuel depot capable of storing 50,000 gallons and pumping 2,000 gallons per minute could be established by 30 engineers in 12 hours. The same installation could be dismantled and relocated in 6 hours, including complete removal of all equipment and restoration of the site to original conditions. More significantly, the portable systems could pump fuel across distances that would require hundreds of truck trips to accomplish using traditional methods. A flexible pipeline could deliver fuel 20 miles from bulk storage to forward positions continuously, eliminating the convoy bottlenecks that had paralyzed operations in North Africa, while reducing the number of vehicles exposed to enemy fire during supply operations. Technical Sergeant Michael O'Brien, who participated in the Fort Belvoir tests, kept detailed notes that survived the war and provided insight into how revolutionary the new systems appeared to soldiers accustomed to traditional methods. The flexible pipelines looked like enormous garden hoses, but they could carry thousands of gallons without leaking, he wrote. The pump stations were small enough to fit on a single truck, but they could maintain pressure across miles of pipeline. The storage tanks looked like deflated balloons when we unloaded them, but they could hold 50,000 gallons when inflated. Production of the new equipment began immediately following successful testing, drawing on American industrial capacity that was already operating at maximum efficiency for war production. Flexible steel pipelines were manufactured by companies that normally produced industrial hoses and firefighting equipment. The pipes consisted of corrugated steel inner tubes surrounded by wire mesh reinforcement and rubber outer coatings that provided flexibility while maintaining strength under pressure. Portable pumps came from firms specializing in firefighting equipment and industrial pumping systems. Each pump station was designed to fit on a standard 2.5-ton truck and could be operated by 2 soldiers after minimal training. The pumps were centrifugal designs capable of maintaining pressure across 20 miles of pipeline while pumping up to 1,000 gallons per minute continuously. Collapsible storage tanks were produced by manufacturers of inflatable military equipment, including life rafts and emergency shelters. The tanks used rubberized fabric construction that could be folded into compact packages for transport, but expanded to hold tens of thousands of gallons when inflated. Special valve systems allowed rapid filling and emptying while maintaining structural integrity under varying pressures. By December 1943, the first mobile fuel depot units were shipping to the European theatre as Allied forces prepared for the invasion of France. Each unit included enough equipment to establish a complete fuel distribution network capable of supporting large-scale combat operations. The standard equipment package included 5 miles of flexible pipeline in 1,000-foot sections, 12 portable pump stations with spare parts and maintenance equipment, storage capacity for 100,000 gallons distributed across multiple collapsible tanks, and all necessary fittings, connections, and control equipment required for field installation. The equipment arrived in Britain during January 1944 as Allied forces prepared for Operation Overlord, the invasion of Normandy. American engineers began intensive training on the new systems, learning installation procedures that would prove crucial during the rapid advance across France following the successful establishment of beachheads. The training emphasized speed and simplicity, since the systems would need to be operated by soldiers with minimal specialized knowledge under combat conditions. Technical Sergeant Robert Walsh, who would later supervise fuel depot construction across France and earned a Bronze Star for his innovations in pump station design, kept detailed training notes that illustrated how different the new systems were from traditional military fuel handling. The portable fuel systems were unlike anything we'd seen in the Army, he wrote. Instead of individual containers that had to be moved one at a time, we could pump thousands of gallons continuously through pipelines that could be installed faster than we could dig foxholes. Instead of fixed installations that took weeks to build, Everything could be moved as combat units advanced. The training emphasized modular construction techniques that allowed rapid assembly under adverse conditions. Every component was designed for installation by soldiers wearing gloves and working in darkness if necessary. Pipeline sections connected with simple coupling systems that required only basic hand tools. Pumps required only routine maintenance procedures that could be performed by mechanics with automotive experience. Storage tanks could be inflated and filled within hours of arrival at a new location using equipment that traveled with each unit. June 6, 1944. D-Day. The first mobile fuel depot units landed at Omaha Beach 18 hours after the initial assault waves had established beachheads and begun pushing inland against German resistance. While combat engineers cleared obstacles and established supply routes from the beach to inland areas, fuel supply specialists began construction of the systems that would sustain the coming offensive across France toward Germany. The initial installation was modest by later standards, but represented the beginning of a logistical revolution. A single pipeline from the beach to a storage area 2 miles inland, where fuel could be distributed to combat units. Storage capacity for 25,000 gallons distributed across multiple collapsible tanks that could be relocated rapidly if German counterattacks threatened the area. Pumping capability of 800 gallons per minute that could supply an entire armored regiment continuously without interruption. Captain Donald Reed, commanding the 1st Fuel Depot Unit to establish operations in France, documented the installation process in daily reports that revealed how quickly the new systems could be deployed under combat conditions. We began unloading equipment at 0800 hours on June 7th, while German artillery was still targeting the beach area, he wrote. By 1800 hours, we were pumping fuel from ships directly to storage tanks inland. No trucks involved in the bulk movement, no individual containers to handle, just continuous flow from ship to tank to combat vehicle. The German response revealed their complete misunderstanding of Allied logistical capabilities and the strategic implications of mobile fuel systems. German intelligence had calculated Allied fuel requirements based on traditional truck transport methods that they understood from their own operations. They expected fuel shortages to limit Allied offensive operations within days of the landing, forcing American forces to pause and consolidate while supply lines were established using conventional methods that required weeks to implement effectively. Instead, American fuel systems were establishing sustainable supply networks faster than German forces could retreat and destroying infrastructure to delay Allied advances. Oberst Wilhelm Hoffmann, responsible for German logistics planning in Normandy, reported to his superiors that Allied fuel distribution appeared to operate by principles unknown to military engineering, creating supply capacity faster than we can target it for destruction. As Allied forces broke out of Normandy during late July 1944, the mobile fuel depot units demonstrated their strategic value in Operation Cobra, the offensive that shattered German defensive lines and enabled rapid advances toward Paris. Tank columns advancing toward the Seine River never experienced the fuel shortages that had characterized earlier campaigns in North Africa and Italy. Portable fuel systems advanced with combat units, establishing new supply points as territory was captured and abandoned installations as forces moved forward. The psychological impact on German forces was as significant as the tactical advantages provided to Allied units. German commanders had been trained to expect that destroying fuel infrastructure would create operational delays measured in days or weeks, providing time to establish new defensive positions and bring up reinforcements. Instead, American engineers were rebuilding fuel capacity faster than German forces could destroy it, creating a sense that Allied resources were truly inexhaustible. General Major Kurt Badinsky, responsible for German logistics in northern France, reported in August 1944 that Allied fuel systems had eliminated the traditional vulnerabilities we expected to exploit. Destroying individual installations has minimal impact because replacement capacity appears within days. The American logistics system appears designed to function despite our interdiction efforts. The operation that would prove the system's revolutionary capability began on August 12, 1944. when General George Patton's Third Army was advancing toward the Seine River at speeds that exceeded all previous Allied operations in Europe. Patton's armor was moving so rapidly that existing fuel supplies were concentrated near the Normandy beachheads, over 100 miles behind the advancing forces. Traditional truck convoys would require days to establish adequate supply lines across that distance while maintaining sufficient fuel reserves for continued operations. Major Patterson's unit received orders to establish advanced fuel depots capable of sustaining Patton's offensive without requiring tank columns to return to rear area supply points for refueling. They had 48 hours to create fuel distribution capacity for an entire army group, advancing at speeds that exceeded all previous Allied operations in Europe. The mission represented the ultimate test of mobile fuel systems under actual combat conditions. The solution demonstrated the full potential of mobile fuel systems operating as integrated networks rather than individual installations. Instead of building a single large depot that would represent a vulnerable target for German attack, Patterson's engineers established a network of interconnected installations distributed across the area of operations. Flexible pipelines connected multiple storage points that could supply each other if individual installations were damaged. Portable pumps maintained pressure across the entire network, while allowing fuel flow to be rerouted without major reconstruction. Construction began at dawn on August 13th, with equipment that had been prepositioned during the Normandy build-up and transported forward as combat units advanced. Trucks carrying pipeline sections, pump stations, and collapsible storage tanks moved toward advanced positions, while combat units were still clearing German resistance from the area. By nightfall, the first pipeline sections were being connected and tested under floodlights that made the construction site visible for miles. The installation process had been refined through months of training and operational experience since D-Day. Pipeline sections unrolled across terrain like enormous fire hoses, conforming to ground contours without requiring excavation or special preparation. Pump stations, each weighing less than 2 tons when fully assembled, could be positioned by single vehicles and connected to pipeline networks within hours of arrival. Storage tanks inflated within hours using portable compressors and began accepting fuel as soon as connections were complete and pressure tested. Sergeant First Class Michael O'Brien, responsible for pump station operations across the network, documented the construction pace in letters home that survived the war. "We had 12 pump stations operational by the morning of August 14th, he wrote to his wife in Michigan. Each station could maintain pressure across 5 miles of pipeline without assistance from other stations. The entire network covered 40 miles from bulk storage areas near the beaches to forward distribution points where tank columns could refuel without interrupting their advance toward Paris. The first fuel reached forward storage tanks on August 14th at 1400 hours, less than 30 hours after construction began, and while German forces were still contesting control of some areas where pipelines had been installed. By evening, fighter aircraft were refueling at forward airfields that had been supplied exclusively by truck convoy just days earlier. Tank columns received fuel continuously without returning to rear area supply points, maintaining offensive momentum that prevented German forces from establishing defensive positions. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. German commanders observing this rapid fuel depot construction concluded that American logistics capabilities exceeded their intelligence estimates by enormous margins that made traditional defensive planning obsolete. The speed of construction defied everything they understood about military engineering. Oberst Heinrich Fischer, commanding German forces near Dreux, reported to his superiors that Allied fuel systems appeared to be installing themselves faster than we can target them, creating a psychological impact that affected German morale as much as physical combat operations. The psychological impact on German forces was significant and measurable. They had been trained to expect that destroying fuel infrastructure would create operational delays that provided time for strategic withdrawal and defensive preparation. Instead, American engineers were rebuilding fuel capacity faster than German forces could destroy it, while advancing combat units maintained pressure that prevented organized withdrawal. This created a sense among German soldiers that Allied resources were inexhaustible and resistance was futile. August 15, 1944. The scene that opened this narrative. Major Patterson surveying a fuel depot that had materialized in a French wheat field with mechanical efficiency that defied traditional military engineering timelines. The installation pumping 2,000 gallons per minute represented the culmination of 18 months of innovation that had transformed military fuel logistics from a limiting factor to an enabling capability for rapid mechanized warfare. Behind the apparent speed and simplicity lay months of detailed planning and preparation that had revolutionized how military engineers approached logistical problems. Every component had been designed for rapid deployment under adverse conditions. Every procedure had been refined through training and operational experience. Every connection had been standardized for compatibility across the entire system, allowing components manufactured by different suppliers to work together seamlessly. The strategic implications became clear during the following weeks, as Third Army's advance toward the German border proceeded without fuel-related delays that had limited previous Allied operations. Fighter squadrons supported ground operations continuously because aircraft could refuel at forward airfields supplied by pipeline networks rather than flying back to rear area bases. Tank columns maintained offensive momentum that German forces couldn't match because fuel was available wherever and whenever needed. By September 1944, American forces had established over 200 mobile fuel depots across France, creating the largest field fuel distribution system ever constructed. The network included more than 800 miles of flexible pipeline connecting installations from Normandy to the German border, 300 pump stations maintaining pressure across the entire system, and storage capacity exceeding 5 million gallons distributed across thousands of collapsible tanks that could be relocated as tactical situations changed. The system's flexibility proved as valuable as its capacity for supporting Allied operations. When German counterattacks threatened specific installations, entire depot networks could be relocated within hours, using procedures that had been developed during training in England. When advancing forces changed direction in response to tactical opportunities, pipeline networks could be reconfigured without starting construction over from the beginning. The mobile systems adapted to tactical changes that would have required weeks to accommodate with fixed installations built using traditional methods. Technical innovations continued throughout the campaign as engineers identified improvements that increased efficiency and reliability. Engineers developed improved coupling systems that reduced pipeline connection time by 50% while maintaining reliability under combat conditions. Pump stations were redesigned for easier transport and faster installation by reducing the number of separate components required for assembly. Storage tanks incorporated better inflation systems and more reliable sealing that reduced maintenance requirements under field conditions. The economic efficiency was remarkable compared to traditional fuel distribution methods. Traditional systems required approximately one truck and driver for every 500 gallons delivered to forward positions, creating enormous personnel and vehicle requirements that strained Allied logistics capabilities. Mobile fuel systems could deliver the same quantity with 1/10 the personnel and vehicles, while providing continuous flow rather than intermittent supply. This freed transportation assets for other crucial supplies while reducing the logistical burden on advancing forces. German attempts to disrupt Allied fuel systems revealed the network's resilience and the effectiveness of distributed design principles. Bombing attacks that destroyed individual pipeline sections could be repaired within hours, using spare components that were stockpiled at regular intervals along the network. Artillery strikes on pump stations resulted in rapid replacement rather than operational shutdown, because adjacent stations could maintain pressure until repairs were completed. The distributed nature of the mobile systems made them nearly impossible to disable completely through conventional military action. General Major Kurt Badinsky, responsible for German logistics in northern France, reported in September 1944 that Allied fuel systems had eliminated the traditional vulnerabilities we expected to exploit. Destroying individual installations has minimal impact because replacement capacity appears within days. The distributed design makes targeting ineffective because damaging one component doesn't shut down the entire system. The liberation of Paris on August 25, 1944, was supported by fuel systems that had been established less than 2 weeks earlier and demonstrated the strategic value of mobile logistics. Tank columns entered the city with full fuel loads that allowed immediate pursuit of retreating German forces. Fighter aircraft provided and continuous air cover because they could refuel at airfields supplied by pipeline networks rather than flying back to bases in Normandy. The rapid establishment of fuel infrastructure had enabled operations that would have been impossible under traditional logistics constraints. As Allied forces approached the German border during autumn 1944, mobile fuel systems continued demonstrating their strategic value during operations in increasingly difficult terrain and weather conditions. The advance through Belgium and Luxembourg proceeded without fuel shortages, despite German efforts to destroy existing infrastructure. Advancing armies maintained operational tempo that prevented German forces from establishing defensive positions because fuel availability never became a limiting factor on Allied operations. The Battle of the Bulge in December 1944 provided the ultimate test of mobile fuel systems under emergency conditions, when German forces launched their surprise offensive that threatened to cut Allied supply lines and recapture territory gained during the summer advance. When German forces broke through Allied lines in the Ardennes, fuel depots in the affected area were rapidly relocated to prevent capture using procedures that had been developed for exactly such contingencies. Within 48 hours of the German offensive beginning, new fuel distribution networks were operational behind revised defensive lines that allowed Allied forces to maintain resistance while reinforcements were brought up. The rapid re-establishment of fuel supply during the Bulge demonstrated that mobile systems could respond to tactical emergencies faster than traditional logistics could adapt to changing circumstances. Fixed installations would have been lost to advancing German forces, but mobile systems were simply moved to new locations and continued operating without significant interruption to Allied operations. By the war's end, in May 1945, American mobile fuel systems had delivered over 50 million gallons to combat units across Europe, representing a logistical achievement unprecedented in military history. The network included more than 2,000 individual installations connected by 3,000 miles of flexible pipeline that had been installed, relocated, and maintained under combat conditions by soldiers who had learned their skills during the campaign. The personnel requirements told the efficiency story clearly. Traditional fuel distribution would have required approximately 15,000 soldiers to deliver equivalent quantities using truck convoys and individual containers. Mobile fuel systems accomplished the same mission with fewer than 4,000 personnel, representing a 3-to-1 improvement in efficiency that freed over 10,000 soldiers for combat duties while providing superior service to advancing forces. Post-war analysis by Allied logistics specialists revealed the strategic significance of mobile fuel logistics in shortening the war and reducing casualties. General Eisenhower's staff calculated that rapid fuel depot construction had shortened the European campaign by approximately 6 weeks by enabling continuous offensive operations that prevented German forces from establishing defensive positions. Tank columns averaged 40% higher daily mileage because fuel was available at forward positions rather than requiring return trips to rear area supply points. Fighter squadrons flew 30% more sorties because refueling didn't require returning to distant bases. The cost-effectiveness was extraordinary compared to traditional military logistics systems. A traditional military fuel depot capable of storing and distributing equivalent quantities cost approximately $50,000 and required several weeks to construct using conventional methods. A mobile fuel depot providing the same capacity cost $6,000 and could be operational within hours of arrival at a new location. The savings in time, money, and personnel were enormous while providing superior operational capability. The technology transfer to civilian applications was immediate and widespread after the war ended. Oil companies adopted military mobile fuel systems for civilian emergency operations when natural disasters or equipment failures disrupted normal distribution networks. Construction firms used flexible pipeline technology for temporary installations during major projects that required fuel distribution to remote locations. Emergency response organizations incorporated portable pump systems for disaster relief operations, where rapid infrastructure restoration was critical. The individuals who created mobile fuel systems received limited recognition compared to those who designed more visible weapons systems, but their achievement was transforming fuel logistics from constraint to enabler of military operations. Colonel Louis Brereton was promoted to Brigadier General and received the Distinguished Service Medal for his leadership in developing the Mobile Fuel Depot program. Major William Patterson was awarded the Bronze Star for his leadership during the French campaign and his innovations in rapid deployment techniques. Technical Sergeant Robert Walsh received the Army Commendation Medal for his innovations in pump station design that increased reliability and reduced maintenance requirements under field conditions. These men and hundreds of others transformed fuel distribution from a limiting factor to an enabling capability that gave Allied forces decisive advantages in mechanized warfare. Their achievement was transforming fuel logistics from constraint to enabler of rapid mechanized operations. Before mobile fuel systems, advancing armies were limited by the speed of truck convoys, delivering individual containers across increasingly long supply lines. After mobile systems were implemented, fuel availability was limited only by bulk storage capacity and pipeline network extent, fundamentally changing the operational possibilities for mechanized warfare. The psychological impact on American forces was equally significant and measurable through improved performance and morale. Tank crews advanced confidently knowing fuel would be available at forward positions without requiring dangerous return trips to rear area supply points. Fighter pilots flew aggressive missions, knowing refueling wouldn't require long flights to distant bases that reduced time available for combat operations. Infantry units received continuous air support because aircraft weren't constrained by fuel availability at forward airfields. German forces experienced the opposite psychological effect as they observed Allied operations that seemed impossible under traditional logistics constraints. Tank columns advanced faster than German forces could retreat because they never paused for refueling operations. Fighter aircraft appeared over battlefields continuously because pilots could refuel at forward airfields supplied by pipeline networks. The apparent inexhaustibility of Allied resources created morale problems that affected German combat effectiveness as much as actual losses of personnel and equipment. The engineering principles that enabled mobile fuel systems remain relevant today in civilian and military applications. Standardized components allow rapid assembly and maintenance by personnel with minimal specialized training. Modular design enables systems to scale from small installations to major networks depending on operational requirements. Portable construction methods allow deployment in areas without existing infrastructure or where permanent installations would be vulnerable to enemy action. Modern military fuel distribution systems trace their ancestry directly to the innovations developed during World War II by the Petroleum Supply Task Force. Contemporary fuel farms use flexible pipeline networks descended from the systems first deployed in France during the summer of 1944. Portable pump stations remain standard equipment for rapid deployment scenarios where traditional infrastructure is unavailable or inadequate. The basic concept of mobile fuel logistics has proven enduringly valuable across decades of military operations. The strategic lesson transcends fuel logistics, specifically, and applies to any complex logistical challenge. The story demonstrates how engineering innovation can eliminate traditional constraints on military operations that seem fundamental, but actually reflect technological limitations rather than inherent physical laws. Creative engineering applied systematically to clearly defined problems can transform constraints into advantages that provide decisive operational superiority. The Mobile Fuel Depot program succeeded because engineers applied civilian industrial methods to military problems rather than accepting traditional military approaches as unchangeable. Petroleum industry expertise in rapid pipeline deployment proved directly applicable to combat situations when properly adapted for field conditions. Emergency response procedures developed for natural disasters worked equally well for tactical emergencies when implemented by properly trained personnel. Cross-pollination between civilian and military technology created solutions that neither domain could achieve independently, demonstrating the value of looking beyond traditional military suppliers for innovative approaches to long-standing problems. The willingness to question fundamental assumptions about how military logistics had to work enabled breakthroughs that seemed impossible under conventional thinking. The program also demonstrated the importance of systematic thinking that treated fuel distribution as an integrated system rather than a collection of individual components. Mobile fuel systems weren't just portable equipment that could be moved from place to place. They were integrated networks designed to function as complete systems where pipeline networks, pump stations, storage capacity, and control systems were all optimized to work together efficiently rather than being designed separately. This systems approach created capability greater than the sum of individual components because each element was designed to enhance the performance of all other elements. Pipeline networks were designed to work with specific pump stations that were matched to storage systems that were compatible with control equipment, creating integrated solutions rather than collections of separate devices. Quality control was crucial throughout the program because equipment manufactured by multiple suppliers had to meet exact specifications for interoperability across the entire system. Pipeline sections from different manufacturers had to connect reliably under field conditions. Pump stations had to maintain consistent pressure across networks assembled from components produced separately by different companies. Standardization enabled the distributed production that made rapid deployment possible, while ensuring reliability under combat conditions. Training programs were equally important because mobile fuel systems required different skills from traditional fuel handling methods. Soldiers learned to assemble pipeline networks rather than simply moving individual containers from trucks to storage areas. They mastered pump station operation rather than basic truck driving and container handling. The transition from individual container logistics to continuous flow systems represented a fundamental change in military fuel handling that required comprehensive retraining of personnel. The documentation that survived provides detailed insight into how major innovations happen in military organizations and how civilian technology can be adapted for military applications. Mobile fuel systems didn't emerge from a single breakthrough discovery, but resulted from systematic analysis of operational problems, creative application of civilian technology, careful engineering of integrated solutions, and continuous refinement through practical experience under increasingly challenging conditions. The timeline from problem identification to operational deployment was remarkably short by military standards, demonstrating that innovation could proceed rapidly when driven by clear operational requirements and supported by appropriate resources. The Tunisia crisis occurred in spring 1943 when operational problems became apparent. Prototype systems were tested by summer of the same year. Production began in autumn 1943. Operational deployment started with D-Day in June 1944, representing an 18-month development cycle that delivered revolutionary capability. The cost-effectiveness was extraordinary compared to traditional alternatives while providing superior operational capability. Mobile fuel depot equipment cost approximately 60% less than equivalent fixed installations, while providing greater flexibility and reliability under combat conditions. Installation time was reduced by 80% compared to traditional construction methods. Personnel requirements were cut by 70%, while providing superior service to combat units. These efficiency improvements freed resources for other critical military needs, while improving operational capability in ways that provided decisive advantages over enemy forces still using traditional logistics methods. The resource savings enabled deployment of additional combat units, while the operational improvements gave those units decisive advantages in mechanized warfare. The environmental considerations were also significant in military operations, where contamination could affect local populations and military effectiveness. Mobile fuel systems reduced ground contamination compared to traditional truck transport that often resulted in spills during loading and unloading operations. Flexible pipelines eliminated fuel spillage during transport across difficult terrain. Collapsible storage tanks could be removed completely after use, leaving minimal environmental impact compared to permanent installations that remained after military operations ended. International adoption was immediate after the war, as other nations recognized the advantages of mobile fuel systems for military and civilian applications. British forces incorporated American mobile fuel technology into their logistics doctrine and used it during operations in Greece and the Middle East. French military engineers studied the systems for reconstruction planning in areas where infrastructure had been destroyed during the war. Soviet forces developed similar capabilities based on captured equipment and technical documentation obtained during joint operations, implementing mobile fuel systems for operations in Eastern Europe and Asia. The innovation spread globally because its advantages were obvious to anyone familiar with traditional logistics limitations. The legacy extends far beyond military applications into civilian emergency response and industrial operations. Modern emergency response systems use descendants of World War II mobile fuel technology for disaster relief operations, where rapid infrastructure restoration is critical. Disaster relief operations employ portable pump stations and flexible pipelines for restoring fuel distribution after hurricanes, earthquakes, and other natural disasters that damage permanent infrastructure. Construction projects use temporary fuel distribution networks based on military designs for supplying equipment in remote locations where permanent infrastructure doesn't exist. Mining operations employ mobile fuel systems for exploration and development activities in areas where pipeline construction would be impractical or temporary operations. Don't justify permanent installations. The story of mobile fuel depots illustrates how engineering creativity can solve seemingly impossible problems by questioning fundamental assumptions rather than accepting traditional limitations. When traditional methods prove inadequate for operational requirements, the solution often lies in fundamental reconceptualization rather than incremental improvement of existing approaches. Mobile fuel systems succeeded because engineers abandoned traditional assumptions about how military fuel logistics had to work. The key insight was treating fuel distribution as a flow problem rather than a transportation problem that required moving individual containers from point to point. Traditional methods focused on moving containers from supply points to consumption points, using truck convoys that were limited by vehicle availability and road conditions. Mobile systems focused on establishing continuous flow from source to destination using pipeline networks that could operate regardless of road conditions and vehicle availability. This conceptual shift enabled solutions that were impossible under the transportation paradigm because it eliminated the fundamental bottlenecks that limited traditional systems. Instead of being constrained by truck availability and road capacity, mobile systems were limited only by pipeline capacity and pump station capability, both of which could be scaled as needed for operational requirements. The implementation required overcoming institutional resistance as well as technical challenges, because military organizations are naturally conservative and reluctant to abandon proven methods for unproven innovations. Military logistics specialists were initially skeptical of systems that abandoned time-tested methods for civilian technology that hadn't been proven under combat conditions. Procurement officials questioned whether civilian petroleum equipment could meet military reliability standards under conditions that exceeded civilian operational requirements. Combat commanders worried about depending on unfamiliar technology in critical situations, where equipment failure could result in operational failure and increased casualties. The natural conservatism of military organizations provided important safeguards against adopting untested innovations, but it also created resistance to necessary changes that would provide decisive advantages. Success in actual operations overcame all institutional resistance because results spoke louder than theoretical concerns. When mobile fuel systems enabled Third Army's rapid advance toward Paris, skepticism disappeared among commanders who saw the operational advantages. When fighter squadrons maintained continuous operations because of forward fuel availability, doubts evaporated among pilots who benefited directly from improved logistics. Performance in combat validated the engineering concepts completely and demonstrated that civilian technology could exceed military requirements when properly adapted. The measurement of success was ultimately operational rather than technical, because the purpose of improved logistics was enabling superior military performance. Mobile fuel systems succeeded because they enabled military operations that would have been impossible otherwise, while providing decisive advantages over enemy forces using traditional methods. tank columns advanced faster because fuel was continuously available without requiring return trips to rear area supply points. Fighter squadrons flew more sorties because pilots could refuel at forward airfields supplied by pipeline networks. These operational improvements translated directly into tactical and strategic advantages that helped win the war. The broader lesson applies to any complex problem where traditional solutions prove inadequate for evolving requirements. Success often requires abandoning conventional approaches entirely rather than trying to improve them incrementally. Revolutionary solutions come from fundamental reconceptualization, not evolutionary refinement of existing methods that are inherently limited by outdated assumptions about what is possible. The engineers who created mobile fuel systems were solving a specific military problem, but their approach demonstrates principles that apply universally to complex challenges. Identify the fundamental constraint limiting performance rather than accepting it as unchangeable. Question whether that constraint is inherent or merely traditional practice that can be overcome with different approaches. Look for solutions in adjacent domains that have solved similar problems using different methods. Design integrated systems rather than individual components that must work together efficiently. Test rapidly and refine continuously based on practical experience under actual operating conditions. These principles enabled American engineers to create fuel distribution systems that German commanders never anticipated and couldn't counter effectively using traditional military methods. Mobile fuel depots gave Allied forces strategic advantages that helped shorten World War II, while demonstrating how engineering innovation can transform military capability by eliminating constraints that seemed fundamental but were actually technological limitations. The wheat field outside Dreux, where Major Patterson watched his engineers work, represented more than rapid construction of fuel infrastructure. It represented proof that creative engineering could eliminate constraints that seemed fundamental, enabling operations that traditionalists considered impossible under existing technological limitations. The transformation of military fuel logistics from limiting factor to enabling capability demonstrated that engineering innovation could change the strategic balance of warfare itself. The story reminds us that the most profound innovations often appear deceptively simple in retrospect, while requiring revolutionary thinking during development. Mobile fuel systems used existing components assembled in new ways, rather than requiring exotic new technologies. The breakthrough was conceptual rather than technological, involving a fundamental reconceptualization of how fuel distribution could work under field conditions. Seeing fuel distribution as a flow problem rather than a transportation problem opened possibilities that no one had previously imagined possible with available technology. This is why the story matters beyond its historical significance and wartime applications. It demonstrates that engineering creativity, applied systematically to clearly defined problems, can achieve results that seem impossible under conventional assumptions about what technology can accomplish. The mobile fuel depots that supplied Allied advances across France proved that limitations often reflect imagination rather than physics, and that creative problem-solving can overcome apparently insurmountable technical challenges. The human impact was equally significant as the technical achievement. Mobile fuel systems enabled rapid victory that reduced casualties on both sides by shortening the war and preventing prolonged fighting across Europe. Tank crews survived because they could advance rapidly without pausing for vulnerable refueling operations. Fighter pilots survived because they could operate from forward airfields without long flights to distant bases. Infantry units received better air support because aircraft availability was increased through improved logistics. German soldiers also benefited indirectly because rapid Allied advances prevented prolonged defensive fighting that would have resulted in higher casualties. The war ended sooner because Allied forces could maintain continuous offensive operations without logistical delays that would have allowed German forces to establish stronger defensive positions. Engineering innovation that enabled rapid victory served humanitarian purposes as well as military objectives. The technical legacy continues influencing modern logistics systems across military and civilian applications. Contemporary emergency response systems use descendants of World War II mobile fuel technology for disaster relief operations. Modern military forces employ portable fuel distribution systems for rapid deployment scenarios where permanent infrastructure is unavailable. The basic principles of modular design, standardized components, and systematic installation procedures remain standard practice for temporary installations. The conceptual legacy may be even more important than the technical innovations. The willingness to question fundamental assumptions about how complex systems must work enables breakthrough innovations that seem impossible under conventional thinking. The confidence that engineering can solve production and logistics problems by applying systematic analysis and creative thinking to clearly defined challenges remains as relevant today as it was in 1944. When Major Patterson stood in that French wheat field on August 15, 1944, watching fuel flow at 2,000 gallons per minute through systems that had materialized in 18 hours, he was witnessing the power of engineering innovation to change the course of history. The German troops, who never expected America's engineers could build fuel depots across France in days, learned that American industrial creativity was itself a weapon of war that could not be countered by traditional military methods. The mobile fuel systems that enabled Allied victory in Europe demonstrated that the most effective weapons are often not the most visible ones. While tanks and aircraft received public attention, the logistics systems that kept them operational determined their actual effectiveness in combat. Engineering innovations that enabled superior logistics capability provided decisive advantages that traditional military thinking couldn't counter or match. The story of mobile fuel depots proves that systematic engineering thinking can solve problems that appear impossible when approached with conventional methods. Creative problem-solving that questions fundamental assumptions can eliminate constraints that limit performance and enable capabilities that transform entire fields of endeavor. The engineers who revolutionized military fuel logistics during World War II showed that the right people asking the right questions can accomplish anything, including changing the outcome of the greatest conflict in human history. The wheat field in France, where this story began, has returned to agricultural use, growing crops instead of storing fuel for advancing armies. But the principles demonstrated there continue influencing how complex problems are solved across countless applications. The confidence that engineering innovation can overcome any constraint if the right approach is applied systematically by people willing to question conventional assumptions remains as powerful today as it was when American engineers proved that fuel depots could indeed be built across France in days rather than weeks. The mobile fuel systems that helped win World War II remind us that the most important innovations often come not from exotic new technologies, but from creative applications of existing capabilities to solve problems in ways that no one had previously imagined possible. Sometimes the best solutions are hiding in plain sight, waiting for engineers creative enough to see past conventional thinking and confident enough to prove that impossible is often just another word for not yet attempted. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.